So I hope my screen is visible to all of you. So you need to open your software that you have installed in the C drive. So here you can see, this is my C drive. And this is my Device Studio 2020A folder. So this is my C drive, and this is my Device Studio 2022A folder. I need to open this folder. Again, you can open this bin folder. So if you want to open this software, you can go to the C drive. You can see this is my C drive. This is my Device Studio 2022A folder. You need to open this bin folder. You can drag and drop. Then you will find this Device Studio application file. You can see this is the Device Studio application file. You can right click and you can run this Device Studio as an administrator. You can select the Device Studio application file and you can run this Device Studio application file as an administrator. Then it will take the permission. Then you can select the yes. And now you can see this is the user interface. So I hope everyone is following the same procedure that I am showing. And here you can select this create a new project. You can select this create a new project. Then you can select this OK. And here you can enter the project name. Here you can enter the project name. Also, you can select the location where you want to save this project. Then you can click on the save option. So if you want to open this software, you can go to the C drive, open this Device Studio 2022A folder. Again, you can open this bin folder. You can go down. Then you will find this Device Studio application file. You need to select this file, right click, and you can run this Device Studio as an administrator. Then it will ask the permission to open. Then you can select yes. Then your Device Studio will be open. So I hope everyone has been opened their Device Studio application file. Here you can see this is my project name, second session. So basically in this session, I will show you how to create any material, any crystal, and how you can simulate that structure by using NANODCAL and RESCU software. So if you want to create any structure, you can select this build option. You can select this crystal builder. So first, I will show you how to create any crystal by using this graphical user interface. And then I will also tell you how to simulate that structure by using NANODCAL and RESCU software. So you can go to the build. Then you can select this crystal builder. And then you will find this interface. So this is the crystal builder interface. Here you can see this is the lattice information like the space group information 1p1, 2p1, 3p2, and this is the previous lattice triclinic. Here you can see this is the ABC value, this is the alpha beta gamma value. Here you need to add the element, then you can go to the preview style. You can see this is the primitive cell and this is the conventional cell. So if you want to create a silicon structure, so first you can select their space group information. So you can go to this space group information. And here you can see this is the space group. And here you can see this is the previous lattice. So this is the face center cubic structure. So from this space group, you need to select this information. Then their previous lattice will automatically selected. So after selecting this space group, you can change the value of A. So here you can change the value of A. So here I am taking 5.1 angstrom. So this is the default parameter. You can include 5.41 angstrom.
Pardon, sir?
Yes, sir, tell me.
Sir, actually, these values are predefined or we have to select?
Sir, you need to select. Here you can see, first I have selected this group.
Okay, let's say we are going for the silicon crystal.
So first you
so
need
why
to
you take
yes.
Yes, this space group. So why you take only 220 FM3? Means it
So
should be
because
defined no, for
yes, because I want to create a face center cubic structure of the silicon. Okay. So that's why I have selected this space group information. And also you can search this material in the import online. Either you can import from the local database. Creating any structure, you should know their space group information, their previous lattice parameter, their ABC value. You should also know their element, their fractional coordinate point. Then you can create any structure. So this information required by creating this structure. So here you can see, this is the value of A, 5.41 angstrom. Then you can go to the element.
So may I? Hello.
Yes, tell me.
Yes, sir. So for hexagonal value, we have to put our value for ABC.
Yes, ma'am. Yes, ma'am. Ma'am, basically in this hands-on, you can follow the same procedure that I am showing. And after this session, you can create your own structure. Then you can do the simulation.
So actually 225 FM3, I'm not getting in this. So that's it.
Okay, no, sir. So participant kindly follow the same procedure that I am showing so that you can do the simulation very easily. And after this hands-on, you can create your own structure. You can define your own parameter. Then you can do the simulation.
Yes, sir, please, let's proceed.
So you can go to the element part. You can select this add option. You can select this 0, 0, 0 fractional coordinate point. And here you can see this default carbon element has been selected. So this carbon has been selected. So we need to replace this carbon with the silicon. So we can do one thing. We can double click on the carbon. Then you will find the periodic table. So from this periodic table, you can select this silicon. Here you can see. This silicon has been selected. Then you can select this OK. Now you can see the carbon has been replaced by this silicon element. So here I would like to create a simple structure, so that I have selected this silicon and their fractional coordinate point is 0, 0, 0. But user can also define your own data. Also, you can add a number of elements from this add option. Here you can see this is the preview style and this is the primitive cell.
Sir,
Yes, sir, tell me.
that 0, 0, 0 is that is orientation or what?
This is the fractional coordinate point, like XYZ position.
Suppose if you create a substrate of the silicon, that is like orientation will be 1, 0, 0 or 1, 0, 1 or like 1, 1, 1 like.
So that is the Miller indices, sir. For the creating a surface, substrate or surface, you need to define the Miller indices, scale value 100, 111, 101. So here, this is the crystal builder. So for creating any crystal, we need to define the XYZ coordinate point.
Okay, okay, thank you.
So you can see this is the primitive cell. Then you can go for the preview. So you can see this is the primitive cell and this is the conventional cell. So you can select this primitive cell. Then you can select this preview. So basically this is the simple silicon structure. So once you define the parameter, you can click on this build option. Then this structure will be built in this device studio. So different structure you can also create from this space group information. And you need to change their Bravais lattice, alpha, beta, gamma value. You need to add more elements. Then you can get the desired structure. Like you can see, this is also the face center cubic structure. If you select this preview, you can see these are the information. So whatever the value you can enter, then you will get the desired output. You can see. So basically your structure depend upon their input parameter. You can see this is the 227, the FD3M. This is the cubic phase center structure. The value of A is 5.41 angstrom. This is the silicon. Their fractional coordinate point is 0, 0, 0. This is the primitive cell and this is the preview. Once you change this space group information, then the structure will be changed. You can see. So this information you can enter, then select this preview, then you can go for the build option. So you can click on this build option. So you can see, this is my simple silicon face center cubic structure. And if you are not aware of the space group information, their ABC value, their alpha, beta, gamma value, then you can import the material from the online database. Here you can see, this is the import online. You can search the material by entering their chemical formula. Here you can see. So you can see this is the silicon with the different space group information. Also, From here, you can get the structure information like their space group information, their cell length ABC value, their alpha beta gamma value, and the atom and their Cartesian coordinate point. So any material you can import from the online database, either you can import the material from the local database. And if you want to simulate this structure, you need to select this simulator. So firstly, I will show you how to simulate with the help of NANODCAL software. And after that, I will show you how to simulate with the RESCU software. So you can see this is the NANODCAL. And this is the self-consistent field calculation. So this is the SCF calculation where we can define DFT parameter. So for simulating any material, you need to select the simulator, select the NANODCAL, then you can select this SCF calculation. Here you can see, this is the SCF calculation. For this is crystal, and we have the basic setting. We can change the electron temperature, cutoff energy, exchange correlation function, LDA, GGA. We can also change the K-point sampling, N1, N2, N3. This is the iteration control parameter like density matrix, Hamiltonian matrix, total energy. Also, you can see this is the basic set. You can see this is the silicon and their neutral atomic database, LDA double zeta polarized. So here I would like to take a default parameter.
Sorry, sir, for
Yes, sir.
interrupting. Actually, what kind of basis set we should choose? Means it is material dependent or user defined?
Sir, user can also define, but if you want to know the theory behind this exchange correlation function, other what you can choose like LDA, GGA, beta GGA, then you can go to this documentation page. And here you can see, this is the document and tutorial.
Okay.
The NANODCAL.
Okay, sir. Yeah, sure. I will go through that.
Okay, sir.
Yeah. Thank you, sir. Thank you.
So you can see, this is the exchange correlation, LDA, GGA. This is the iteration control. This is the basis set. And this is the spin type. So in the spin type, you can select this collinear spin. So here you can see, I would like to select this collinear spin. And this is the spin polarization value for this silicon element. So you can include the collinear spin. So basically, I am telling you a basic procedure for simulating any material. But if you want to define your own parameter, you can also include from this interface. Either you can change the electron temperature, you can change their cutoff energy, you can change their exchange correlation function. You can also change the K-point sampling, iteration control parameter, you can also change. You can also change the spin type. Either you can change collinear spin, general spin, and no spin. So this is the basic idea for simulating any material with the help of NANODCAL software. So whenever you define the parameter, then you can go to the generate file. And now you can see the file has been generated. So this is the project explorer where the input and output file will be there. So you can select this arrow. Again, you can select this arrow. Then you will find this scf.input file. And this is the self-consistent field calculation input file where we have defined the parameter. You can also change the value from this input file. Like you can see, this is the scf.input file. You can select, then you can right click. You can select this open with. So if you want to show the script for this scf.input file, you need to select this input file, right click, select this open with. Now you can see this is the script for this silicon simple structure. Here you can see this is the basic setting. You can also change the value from here. Like if you want to define 100 Kelvin temperature, you can include 100. Then you can save this input file from the save option. You can see this file has been saved. So either you can change the value from this script, either you can change from the user interface. So I hope everyone has been generated their scf.input file. So after generating this scf.input file, you can go for the simulation. So for simulating this structure, we need to select this input file, scf.input file. You can right click, then you can select this run option. Here you can select this run option to run this job. But you can also run this job on parallel. Suppose 5 core, 10 core, 15 core. So there is no limitation of core. You can define up to 128 core. So in the hands-on, we have given you the evolution license. So you can utilize a single core. But whenever the, yes.
Actually, sir, this core depends on computer configuration or
Yes, computer.
we can depend on. Okay. I am using Ryzen 5. So it is showing only maximum 8 cores.
Yes, sir. So sir, basically it depends upon the system.
Okay. Thank you, sir.
In my computer, you can see 12 core is there. But from this evolution license, I can utilize a single core. Here you can see one is selected. So in the paid version, you can utilize all the core during the simulation. So simply you can select this run option to run this job. Now you can see the scf.input file is in the running condition. So firstly, user will run the scf.input file. Then you can go for the analysis. Because in the scf.input file, we have defined the DFT parameter. So based on the DFT parameter, we can go for the analysis. And for analysis the parameter, you can go to simulator, select NANODCAL, then you can go to this analysis. So for analysis the various properties for any material, you can go simulator, select NANODCAL, then you can tap on the analysis. And you can see these are the various analysis parameter. that you can simulate from the NANODCAL. I will also tell you how to simulate this structure with the help of RESCU. So you can see these are the different analysis parameters. For selecting any analysis, you need to double click. Like you can see, this is the density of state. You can double click on this, then it will be selected. Here you can see it has been selected. And in the density of state, you can see these are the parameters. We need to change their K point sampling. If you change the K point sampling, N1, N2, N3, then you will able to get the plot. If you select the 1, 1, 1, then the graph will not be plotted. So you need to select some K point sampling. Like here you can see, I have selected 3, 3, and 3 for the N1, N2, and N3. So this is the density of state. Simply you can go for the band structure. You can see, you can double click on the band structure, then it will be selected. Again, here you can double click, then you will find the parameter for the band structure. First, you can double click on this analysis. Then you can double click on this calculation selected. Then you will find the parameter. Also, if you want to show the Brilliant zone path, you can click on this path option. Now you can see this is the Brilliant zone path for this silicon simple structure. Again, you can select this Hessian so that you can do the Funan band structure. Before simulation of this band structure, we need to select this Hessian. Now you can see the Hessian has been selected. And you can see this is the Hessian parameter. Like this is the delta value. This is the order of this Hessian. And this, then you can go to the Funan band structure. Again, you can see this is the electron density. This is the potential. Here you can see this is the effective potential. You can also change Hartree potential, exchange correlation potential, and neutral atom potential. And this is the transmission channel. Here you can see this is the eigenstate. So whatever the analysis parameter you want, you need to select, you need to define their parameter. Then you can click on this generate file. Here you can see 8 analysis parameter has been selected. So I would like to click on generate file. In the job manager, you can see the scf.input file has been completed. Also, you need to run the analysis input file. You can see these are the analysis input file. We need to run all the analysis input file. So for running any input file, we need to select that file, right click. We need to select this run option. Here we need to select this run option to run this job. So you can run all this analysis input file in the queue condition. So like this is the band structure. This is the Hessian. This is the Funan band structure. This is the electron density. This is the potential. This is the transmission channel. And this is the eigenstate. Here you can see I have run all the analysis input file in the queue condition. When this density of state will be completed, then this band structure will start automatically. So in the same way, you can run multiple input file. And whenever the simulation completed, then you will get the output file. So I hope everyone has been run their input file for this silicon simple structure. And once your simulation completed, then in the project explorer, you will find the output file. Here you can see, I have taken a simple silicon structure, but whenever you increase the number of atoms, then the simulation time will also increase. So to reduce the time, I have selected this simple structure and I have simulated with the default parameter. Whenever you define the exact parameter, then you will get the exact output. Here you can see density of state and band structure has been completed. So if you want to get the plot, here you can see the density of state.xml file and band structure.xml file has been generated. So these are the output. If you want to open this file, you need to select. You can right click. You can go to the show view. You can see this is the density of state with respect to energy. In the input file, you can see I have defined the collinear spin. So this is the spin polarization. This is the collinear spin. So whenever you define the Spintronics application, here you can see this is the spin up graph of this density of state. So this is the spin type. You can also show the spin down. You can see this is the spin down density of state. So this is the spin up density of state with respect to energy for the simple silicon structure. And in the spin type, you can select this down. So this is the spin down. Also, you can select this both spin up and spin down simulation.
Actually, sir.
Yes, sir. Tell me.
Actually, do we need to run these parameters after generating of the log file for SCF file, or we can start it before getting the result for SCF input file?
No, like here you
I
can
hope
see.
you are getting what I'm saying. Yeah.
Yeah.
Like we run these parameters. First we got this out log test file for this SCF input files. So I just want to know, do we need to run these extra parameters like density of states and all these parameters after generation of this log file, or we can run it before obtaining this log file?
Sir, first you need to run the SCF.input file.
Yeah, exactly. Then we get the result. Okay.
Yes. In
Okay,
the meantime,
we
you can
can
also run the analysis. Yes.
Okay. Means there is no need to wait for the log file.
No, sir.
Right. Okay.
But we need to run the
Okay, like
SCF.
in my case, in my case, SCF file is still running. Means although I got the log test file, but it's still running. It's
Yes.
taking too
In
much
the
time.
meantime, you can. Yes. In the meantime, you can also run the
Yeah.
analysis.
Meantime, I have run all the files.
Okay, sir. No issue.
Okay. Thank you.
So this is the density of state plot for the different spin up and spin down simulation. Yes, sir.
Hello, can I use cobalt in antimony alloy instead of silicon? If I
Yes,
have
sir. Yes, sir. You can create the alloy structure as well. So from this crystal builder, you can create the alloy structure by entering their space group, previous lattice, ABC value, alpha, beta, gamma. then you can build this structure. Either you can import that structure from the online database or local
So,
database.
Can import any type of metal oxide or alloy or useless
Yes.
alloy?
Yes,
type.
here you can see. Yes, you can see this is the metal oxide.
Okay.
This is the material, 3D material, and this is the metal oxide.
Okay, okay.
So simply any structure you can select, like you can see, any structure, like this is the aluminum and oxygen, you can see. And then you can create the RESCU input file first. You need to generate this input file. Then you can go to the analysis. So any
But how
structure you
can
can create and run.
How can we select the K points?
Yes, sir.
How to identify K points of corresponding metals? Means alloys.
Like there keep on sampling are some LDA function, exchange correlation, LDA, different fact.
Okay, okay. Okay.
Like here you can see, these are the parameter I have taken for the default option. But you can also change this value.
Oh,
So
yes.
is it possible to design Ti64, titanium 6 aluminum 4 vanadium?
Yes, ma'am, you can create. First, you can search that material in the database, local database. Then you can search the material from the online database. If it is available in the local, then you can import. If it is available in the import online, you need to import. But if it is not available, then you can create your own structure from the build option.
Okay.
So if you have already one zip file, we can just directly import from our
Yes, zip
computer.
file you can zip file you can directly import. Here you can see this software support this file format. So if you have this file format, then you can easily import. Like this is the .sjw, .xyz file, .cif file, .xsd postcard file, content file, escf.input file. So all this file you can directly import.
So
Oh, yeah.
where we get these files from the website?
Yes, you can also get. Like if you want to import some zip file, you can see. I can download the zip file from the material project. Like if here you can see, this is the silicon dioxide. I think I have already downloaded this file. Here you can see, one second.
So it is like MD layer. So if I have the potential, then you in MD, if I have potential, then you will run the program. So in this, that only, if you will get fired, then only you can run this simulation, right?
Yes, ma'am. Either you can import that file or you can create your own file in this device studio. If you want to create your own, then you can go to this build option, select crystal, and from this, enter in all the information you can create. And also you can import the file from our database. You can see these are the database. Either 0D, 1D, 2D, 3D, and organic material. You can see different material are there. Like this is the layer material. If you want to import arsenic, bismuth, boron nitride, also you can see this is the MOS2. WSET is also there.
Is there any data for titanium?
One second, I can search. Yes, you can see.
Okay.
And also you can create this structure as a supercell. So if you want to create this structure as a complex or supercell, then you can go to this build option, select redefine crystal. And this is the redefined crystal by expressing the initial vector UVW as a linear combination of ABC. So whenever you define, like this is the 2, 2, I want to include 4. You can see.
Okay.
So different structure you can create.
So there we can give the composition of the crystal.
Yes, ma'am. Yes, ma'am. You can give.
Thank you.
Here you can see. This is my structure that I have simulated. The density of state. Also, you can see I have get their band structure plot. You can see. This is the band structure for this silicon simple structure. So here you can see. This is the spin up. This is the conduction band. This is the valence band. And this is the Fermi energy. And here you can see these are the energy in the electron volt. And this is the symmetry K point. In the spin type, you can see this is the spin up. This is the spin down. And this is the spin up and spin down.
Only spin down is visible.
Yes,
Blue
sir.
color, blue color is not blue color black band is not visible. In spin up is
Yes.
blue color, spin down is red color. Only spin down is showing.
So they are overlapped to each other because the spin up and spin down are same. These are for the spin up and spin down are same. So they are overlapping.
Okay.
So you can see this is the phonon band structure. So I hope everyone gets their output after their input file completed.
Sir, can you show that this band structure to import in this MATLAB to know
Yes,
the
we
band
can.
gap of that?
Yes, we can import. Here you can see this is the band structure.xml file. We can select that file, select open containing folder. Here you can see this is the XML file and this is the band structure.mat file. So this is the .mat file. You can go to the MATLAB website. You can see this is the MATLAB. You need to create an account and then you can log in. Here you can see. Then you can use the Open MATLAB online and this is the free for any user. Now you can see this is my MATLAB online. You can see this is the band structure.mat file. We need to select.
Sir,
Yes.
it is not coming that band structure is not coming directly in MATLAB.
Here you can see I have selected this band structure. We can select that file. Then we can import into the MATLAB. Here.
Okay, directly we can do it. Huh?
Yes. Now you can see the file has been uploaded. You can double click on this band structure.mat. Here you can see this file has been selected. And here you can tag the command data and press the enter. Now you can see this is the structure information. Like this is the crystal structure and this is the face center cubic structure. Here you can see this is the primitive cell. This is the number of K point. This is the coordinate of K point. This is the symmetry K point. This is the symmetry K point index. This is the Fermi energy. This is the band energy. This is the top of the valence band. This is the bottom of the conduction band. And this is the band gap value.
Sir, is there any other method to directly come to that? It is not coming in my MATLAB in online.
So, sir, do you have imported this file, band structure.mat file?
It is not coming, sir, actually there. That is the
1 second. Here you can see, you can select that file.
okay, sir. Band structure. Yes, sir. Selected. XML, not Microsoft. Okay.
Mat file,
Selected.
mat file you
Ah,
need to select.
Yes.
Here you can see this file selected, and I would like to import into MATLAB. You can open this MATLAB. Here you can see, in this box we need to import. Here you can see. So this is the same file that I need to replace. Here you can see the file has been uploaded.
Okay.
And after importing this band structure.mat file, you can double click, then it will be loaded. Then you can type this command data, then press the enter. Then you will find the output value, their band gap value, their bottom of the conduction band, top of the valence band, their band energy, and their Fermi energy. You can also get the description. You can say this is the description for this band structure. Here you can type data dot description. Then press the enter. Now you can see this is the band gap information, bottom of the conduction band information, top of the valence band, the band energy, the Fermi energy. So all these information you can get from the mat file. And these value are in the Harty. Here you can see this band gap value are in the Harty unit. And in the graph you can see, and these value are in the electron volt. So you can see all the analysis input file has been completed and their output file has been generated. So this is the total electron density .dsf file. You can see. This is the ICO surface in the 3D view. You can see this is the 2D view along x-axis, y-axis, and z-axis. You can also plot in 1D. You can see this is the 1D view. In XY plane, YZ plane, and XZ plane. So this is the total electron density for the silicon face-centered cubic structure. Also, you can get the effective potential, Harty potential, exchange correlation potential. So here you can see, I have generated the effective potential. So this is the output of effective potential for this silicon. So this is the 3D view. This is the 2D view. And this is the 1D view. Also, you can see this is the transmission channel. You can see this is the spin-up transmission channel. This is the spin-down transmission channel. And this is the spin-up and spin-down transmission channel. And you can see this is the total transmission channel with respect to energy. And here you can see this is the eigenstate. Also, you can see this is the band value. This is the 2D. And this is the 1D. So I hope everyone gets their output after simulating this structure. And if anyone facing any issues while simulating any structure, so you can drop your error in the WhatsApp group so that we can take the access of your system and we will solve your issues. So you can see this is the simulation by using the NANODCAL software. That is a Atomistic quantum transport simulator based on the DFT plus the NEGF method.
Band structure. Please
You can see this is the band structure.
Yes, sir.
Yes.
Sir, on band structure.
Yes, this is the full nanomaterial structure.
Yes, yes. Okay. Thank you, sir.
So once your simulation will be completed, then you will get the output file. You can see this is the project explorer where your input and output file will be there. So this is the simulation procedure with the help of NANODCAL software. If you want to do the simulation with the RESCU, real space electronic structure simulation, then either you can select the material from the local database, either you can import the material from online, then you can go for the simulation. Suppose if you want to import some material from this local database, you can select the file, you can select this import option, then you can select this import local. So if you want to import some boron nitride from our existing database, so you can select this file option, you can select the import, then you can select the import local. So you can see this is the material database. You need to select the 2D material. Again, you can see this is the novelty material. Here you can see this is the boron nitride input file. So for importing the boron nitride, you need to select this file, select import, go to the import local, then your material folder will be open. And in the material folder, you can open the 2D material, select the novelty material, then you will find the input file of the boron nitride. You can see this is the boron nitride. So you can select this boron nitride, select this open. You can see this is the boron nitride. So after importing this boron nitride, if you want to simulate this structure with the help of RESCU software, then you can select this simulator. You can select this RESCU, and in the RESCU you can see here you can define DFT parameter in the self-consistent field calculation. And if you want to optimize any structure, you can see this is the relax, that is for optimizing the structure. So in the relax, we have different method, quasi-Newton, stupid descent, and conjugate gradient. Also, we have the molecular dynamic in the NANODCAL. You can select this DFPT. So this is basically a density function perturbation theory. So you can see, you need to select this DFPT. Then you will find this interface. So you can see this is the basic setting. So in the task, you need to select this Raman property calculation. So here you can see this Raman property calculation has been selected. So you need to select this Raman property calculation. You can see this is the simmering sigma. We can define their resolution. We can define the SCF method. And you can see this is the exchange correlation. You can see this is the K point sampling N1, N2, and N3. So for the boron nitride, I would like to generate their input file for the Raman property calculation. We can select this Raman property calculation. Go to the iteration control. You can see this is the iteration control. And in the iteration control, we have the SCF parameter. And also we have the DFPT parameter. So basically these are the DFT parameter in the SCF. And this is the DFPT parameter in the like Sternheimer and Chebyshev filtering. Then you can go to this basic setting.
Sir,
Yes, sir.
what's the difference between NANODCAL and RESCU software?
So basically,
What
sir, yes.
I think what the same procedure is this? Is this the same procedure?
Sir, basically the RESCU software is for the dedicated for the material simulation. So for any material you can simulate with the help of DFT and density function perturbation theory. But the NANODCAL software is dedicated for the material as well as device simulation. Based on the DFT plus NEGF method, you can simulate.
So device stimulation is based on RESCU or nano?
No, NANODCAL.
Nano.
You can see this is the iteration control parameter. This is the basis set where we have the boron and nitrogen and their pseudopotential file. This is the double zeta polarized. This is the Spintronics application. And here you can see this is the Raman parameter. Like we have the damping factor, we have the Q point Cartesian, income photon polarization, outcome photon polarization, income photon wavelength, and temperature. So as per your research work, you can define the input parameter. Then you can click on this generate file. So after defining all these parameters, basic setting, iteration control, basis set, spin type, and Raman, you can go for the generate file. Now here you can see. Yes.
Sir, can we do the magnetic property of material like
Which property? Can you repeat?
magnetic property?
Yes,
Magnetic.
magnetic property you can simulate from the NANODCAL.
Okay.
Like here you can see, we have the ZT where you can calculate the thermoelectric property, magnetic properties for any material.
Okay. For
Sir, we can apply magnetic field to this.
Yes, magnetic field.
We can apply.
Yes, magnetic property you can simulate. Also, you can apply the magnetic.
so, sir,
Yes.
how can we define the antiferromagnetic and ferromagnetic property of material by using this software? Can we draw MH graph, empty graph, like?
Sir, 1 second. Here you can see. Here you can see, this is the ferromagnetic and this is the antiferromagnetic. These are the structure. So this is structure I will cover tomorrow because today's session is basically for the material simulation. Also you can see these are the plots. You can see this is the band structure for the antiferromagnetic and this is for the ferromagnetic.
Okay.
So the simulation is possible from the NANODCAL.
Okay. Thank you.
So you can see this is our hybrid boron nitride structure. And I would like to simulate from the RESCU software. Here you can see I have generated their input parameter like their SF.input file, dielectric.input file, phonon.input file, and Raman.input file. So I hope everyone has been generated this DFPT input file. So after generating this file, we need to run from the top to bottom. So basically first we need to run the SF.input file. Then we need to run this dielectric.input file. Then you can go for the phonon. Then you can run this Raman.input file. Now you can see the simulation is running in the Q condition. Here you can see the SF file has been completed. And now the dielectric.input file is in the running condition. And for their background simulation, here you can see this is the RESCU log.output folder. You need to open this folder. You can see this is the open with 1 second. And here you can see This is the beginning of this self-consistent field calculation. And this is the step-wise step procedure for simulation. You can see this is the total energy, this is the row density, and this is the time taken by this software. Now you can see this is the DFPT dielectric simulation. It has been simulated. And now this phonon.input file is in the running condition. Now you can see this simulation has been completed. So you can select any file, like you can see this is the sf.input file. You can right click, select this open containing folder. You can see these are the input file, SF input file, Raman input file, Phonon input file, and dielectric.input file. And you can see this is the result folder. In the result folder, you can see this is the real space density. This is the dielectric output file. This is the Phonon output file. Yes, sir.
Sir, how can you take this result into our publications? Can I type directly or while using origin proof? How to draw these whole graphs?
Yes, sir. These are the mat file. You can convert that file into text. Then you can import into the origin.
Is these results are possible to publish our work?
No, sir. No, sir. Basically, this is the commercial software. So for for publishing any paper, you need to purchase. Because as you know, this is the evaluation license that we have given to you.
Okay.
So basically, this is the for education purpose, not for the publishing the paper.
Okay. So for the publications, we need to buy software.
Yes. Because this is the commercial software that is developed by Nanotechnology.
Okay. How much is it cost?
So basically, the price depends upon number of users and the validity of the license. Like we have multiple options: 1 year license, 3 year license, 5 year license, and perpetual license also we have. And also we have the 1 year single license, 5 license, 10 license, 20 license. Here you can see this simulation has been completed and their mat file has been generated. But if you want to get the plot for this Raman spectrum, then you can open this input file, Raman.input file. You need to select, right click, select this open with. Now you can see this is the input file. And basically here we need to write a command to get the plot. Here you can see, I would like to write this command to get the plot. So you can see, you need to write RESCU space -p space. You need to copy the location of the file. Here you can see, this is the location of this file. You need to copy and here you can paste. Also you can see it has generated the mat file. So we need to include .mat. So you can see this is my command that I need to write for getting the plot.
Okay, thanks. Thank you, sir.
After writing this command, you need to click on this save file. Then this file will be saved. Here you can see this file has been saved. Again, you need to run this input file. Again, you need to run this. Only Raman input file you need to run. And whenever this simulation completed, then it will generate their plot, like their Raman spectrum, Raman spectrum. You can see the graph has been plotted. Again, you can select this input file, select this open containing folder. Here you can see this is the hybrid boron nitride plot for the Raman Everest polarized graph. This is the polarized graph and this is the Everest Raman spectrum. You can see this is the MATLAB figure. Again, we need to import this file into MATLAB. You need to select this
Sir?
file. Yes.
Can we get IR, infrared, or this NMR spectra also with the
IR
help of this software?
Like IR intensities.
Yeah, infrared.
Yes, you can
Yeah,
simulate.
yeah, exactly.
Yes, you can simulate.
Okay. Thank you, sir.
So IR basically you can get from the optical property.
Okay.
So here you can see I have simulated this Raman property, but whenever you simulate this DFPT in the task, you can select this optical property, then you will get the IR intensities. Also, you can get the photon energy loss, dielectric permittivity, refractive index, all these plot you can get.
Okay, sir.
So here you can see this is my Raman plot. So you can see this is the Raman intensities and this is the Raman shift. So this is the Raman polarized graph. And if we talk about this Raman Everest polarized graph, so you can see this is the plot that we need to import into MATLAB. Again, you can double click and you can see this is the Raman Everest polarized graph. You can see this is the higher peak and this is the lower peak. You can also get their value. So different simulation you can study from this NANODCAL and RESCU software. Optical property, Raman property, phonon density of state, phonon band structure for the RESCU. And if we talk about the NANODCAL, then you can calculate multiple properties like density of state, band structure. All these property you can simulate from the NANODCAL software. So these are the material properties. And tomorrow's session I will cover on the device properties, like how you can create any device structure, how you can define their left electrode, right electrode, top electrode, bottom electrode, front electrode. Also how you can define the gate terminal, and then how you can do the simulation.
Okay, sir.
So if anyone has any query regarding any simulation procedure or any material for the RESCU and NANODCAL, so you can unmute your mic and ask me the queries.
Sir, I have one question. One of the user also saw the interest or curious. So can we have the answer tomorrow? That can we simulate in presence of some solvent? Like we have any material and we want to know its property in presence of a solvent. Is it possible?
Yes, sir, you can do. You can study that property as well.
Okay.
Yes, any material you can create. Either it could be alloy, any material like cobalt,
Yes, sir.
any material. It could
It's
be.
not about pure material. Actually, I want to curious to know whether can we check the property of a material in a solvent, in presence of a solvent.
So tomorrow, basically, I cover that point tomorrow.
Okay. Yeah. Sure.
So as you know, the validity of this software is 2 months. So you can evaluate our software as much as you can. And also you can create your own structure, either simple structure, complex structure, any parameter you can define. So as per your research work, you can define the parameter, you can do the simulation. And also you can visit our website for the document and tutorial. This nanoacademy.com you can visit. In the bottom of the page, you will find the document and tutorial. And if we talk about their videos, like you can visit our website, Impulse Technology. Impulse Technology Innovative Research you can visit. And also you can see we have the playlist where we have the RESCU, QTCAT software, RESCU software video, Laos, NANODCAL. You can see this is the NANODCAL. So step-by-step procedure are mentioned in the video. And also you can go to the RESCU. You can see this is the RESCU documentation video, like optical property calculation. This is the webinar video. This is the Raman spectrum calculation, Funan band structure, Funan density of state. So if any participant has any query, so you can ask. So this is the commercial software unit. Also you can check various publication paper that is available on the Google Scholar page. So basically this is the education license, so that you can evaluate only, not publish any paper. Like if we talk about the NANODCAL paper, you can type NANODCAL and then you will find multiple publication paper.
Okay.
Like you can see, this is the perfect spin filtering effect. You can see this is the device structure. These are the band structure. You can see this is the IV simulation.
So, sir, if you are studying all this and having no commercial license of this NANODCAL software, so we don't have that much of money to buy this commercial license. So after studying all this, it cannot.
So you can yes, you can discuss with your professor regarding this tool, and they can plan either from the department funding, project funding. So they can plan. Then you can do the publication. So these are the RESCU publication paper, NANODCAL publication paper. And here if you type RESCU, you can see.
Sir, basically RESCU and NANODCAL measure the different property or same property.
Sir, basically RESCU is for the material simulation, not for the device simulation. And RESCU is based on DFT plus density function perturbation theory. But NANODCAL is for the material as well as device simulation.
Okay.
For device simulation, you can study from the NANODCAL based on the DFT plus ENEGF method, non-equilibrium green function theory.
Okay.
Like a RESCU, here you can see these are the different analysis parameters. In the RESCU, you can see these are the parameters that you can simulate, but that property you can simulate from the NANODCAL software.
We cannot find this property in NANODCAL, correct?
These are the RESCU properties, RESCU.
Okay, okay.
And here you can see these are the NANODCAL properties. These are the NANODCAL.
Okay.
Basically, the electrical and electronics property you can simulate from the NANODCAL, and the electronics and optical property you can simulate from the RESCU. So electrical property is not for the RESCU software. Also, you can see this is our website, and here you can see this is the technical insight. In the technical insight, you can also get the publication paper. Here you can see this is the product. Either you can select NANODCAL, RESCU, or QTCAT. Here you can see these are the RESCU, and these are the publication papers. You can see this is our website. So this is the official website, and this is our website, NanoDCAL, Impulse Technology. Here you can see this is the NanoDCAL product. This is the Fluxim product. This is the Metra product, and these are the training program.
Sir, how can we buy this commercial license software? How can we buy?
Sir, we are the sole distributor. So
Okay.
there is no distributor for this.
So I have to contact Impulse Technology for this software, right? Okay, thank you.
Okay, sir. Okay. So thank you so much to all of you for joining this presentation. So tomorrow's session will start from the 11 a.m. And tomorrow I will cover on the device simulation from the NANODCAL software.